Yeah, so I guess we can start. So can you guys please confirm whether am I audible or not? You can ping in the chat if possible. Yeah, thank you, ARV. And also, can you please confirm whether the slides are visible or not? Thank you again. So let's start with our session today. So myself, Ritura Singh Sujawat, I am currently working as a Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. This is the These are the sessions which run in parallel to your regular NPTEL courses. So this particular course basically concerns with the geotechnical engineering too, which is a foundation engineering. The main tutor for this course is being tutored by Professor Dilip Kumar Bedia, who is professor in Department of Civil Engineering from IIT Kharagpur. So let's like before going further, I want to know from where all our learners what are the background of our learners are. So if you guys are comfortable, one by one, can you please unmute yourself and you can just tell me your full name and what is your current educational background and why you have opted this course. So okay, if you guys are comfortable, then only it's fine. So let's start with our first learner, which is there on my screen. So ARV, I think you had joined this course earlier also, right? Yeah, but then also like I like to uh, uh, get to know you. So can you please unmute yourself and introduce yourself?
Yeah, good evening, sir. This is ARV.
Yeah,
You thank you for guessing me.
yeah.
I was one of the faculty actually.
Oh yes, yes.
I used to update my knowledge continuously in the subject. That's why I used to join this course.
Thank you for coming
Thank you,
back
sir.
again. I hope we can continue with same enthusiasm which we have left it earlier.
Yes, sir. Yes, sir. I remember. Thank you, sir.
Thank you, Yash. Moving to our next learner, we are having Mosam Suryavanshi. Can you please unmute yourself and introduce yourself? Mosam, whether it is possible for you to unmute yourself? No worries. Okay, it's fine. No worries. So you can just ping in the chat box if possible, your affiliation and why you have opted this course. Meanwhile, we can move to Vishal. Uh, Vishal, can you unmute yourself? Mm, yeah. So, can you please introduce yourself, Vishal? What is your current affiliation and why you have opted for this course?
I am Tapunas. I am working in West Bengal PWD.
Okay, Tapan. So, you are currently working as a government employee in West Bengal, PWD, right?
Hello, sir.
Yeah, Tapan. Am I audible?
I enrich my study regarding this subject for my profession.
Uh, okay, Tapan. I think your voice is breaking, but it's fine. Thank you for joining this course, Tapan.
Problem, please kindly.
Moving to our next learner, Sudhanshu. Can you unmute yourself?
Yes, sir. My name is Sudhanshu. I'm pursuing right now BTech
Okay,
from Pune.
Sudhanshu from Pune. Great.
Yeah.
So, in which year of your BTech you are? Like,
Third year, sir.
okay, you're in third year. So, is it a part of your regular academic course, or you have just opted like for the gate preparation or any other reason?
No, sir, for GATE preparation.
Okay.
And simultaneously with the foundation engineering, right now we are studying foundation engineering. That's why I was doing both
Okay, okay,
course and also.
okay, Sudhanshu. Okay, thank you for joining this call. Uh, then I think we have done with ARV, Mosam, Sudhanshu. Next we have Sumant Kaur. Sumant, can you unmute yourself?
Yes, sir. I am as a working professional, sir.
Okay,
I am working as a research engineer in some consultancy organization.
okay, great,
For
Sumant.
that
So,
purpose,
if I may ask further, like, what does your consultancy do? Like, in which type of projects are they involved in?
yes, sir. Yes, sir. RVB, sir. Road over bridges and railway construction projects, sir. Bridges and everything, tunnels and everything. Sir.
Okay,
ROBs, like that, sir.
oh, that's great. So, in this course, like, so usually we comes from the academic background, so we can share the
Yes, sir.
information till the extent like which we have from the academic background. So in case in between, if you feel like there are something which you want to share uh, about your experiences, let's say from the field end, so please feel free to unmute yourself and share your experiences with other learners as well.
Sure,
So,
sir.
so
Okay,
we are
sir.
having these sessions are meant for the interaction only. So it's not like
Okay.
I'll teach from my end. So if you have something to share, please feel free to share
Yeah.
in this session.
Sure, sir.
Okay,
Sure, sir. Thank you, sir.
thank
Thank
you so much. Thank you. And further, then we are having Suman, Tapan, Vishal. We have done. I guess we have done with everyone. Anyone is left? So I think we have covered everyone, but in case if anyone is left, please unmute yourself and introduce you.
Sir, some people they mentioned in the chat box. Please go through.
Yeah. Okay. Yeah. So we are having Mosam. Okay, Mosam. Mosam, can you please let us know like what is your current affiliation? Are you a student or a working professional? From chat box only. It's fine. Okay. Meanwhile, we can read the intro of Vishal. So Vishal is basically pursuing masters from Sri Vaishnav Institute of Technology and Science, Indore. It's great, Vishal. And college gives us double O as what it is, Vishal. Okay, okay, guys, it's fine, it's fine, no worries. So it's we can interact in the further sessions also. There's no compulsion. Okay, guys, it's fine. So I think we can move to our session now. So thank you so much for sharing your background, and let me start with our introduction of the session. So once again, welcome to this particular session. So this course is basically geotechnical engineering to foundation engineering. So let me tell you what are the objective of this session particularly meant for. So in these sessions, we are basically deciding to interact with our learners. We'll be discussing some of the important concepts. So you guys will be getting the regular. You guys are getting regular assignments after uh, like at the end of every week. So we'll be discussing some of the important concepts concerning with those assignment problems, so that you it will help you in solving your particular assignment questions. Also, we'll be solving some of the sample questions which are like similar to your assignment problems but not exactly like your assignment problems, so that you can raise your query related to those assignment problems, and then we can particularly address those queries in our sessions here. Also, apart from this, we'll be solving some of your doubts, let's say concerning with any session with any lecture part which you have seen in the NPTEL lectures, and if you want to discuss it, we'll definitely discuss it here. Apart from that, if you want to have any query like related to the course, or let's say not related to the course, and it let's say at the technical end, since we are sitting in IIT, so we are having exposure to some facilities, some resources. So, and also we are having exposure to some guidance as well. So, in that case, if you guys feel like if you want to get to know something about anything like that, and if you want us to share those exposure experiences to you, please feel free to interact. So we'll be solving some of the assignment problems related to the first week. So first week basically are having the assignment problems which are just concerned so that you can brush up your soil mechanics concepts which you have learned, let's say in the previous semester for the bachelor people, or like for the working professionals. It's just a brush up of your soil mechanics concepts which are going to be applied in our foundation engineering questions. So let's move further. So here is the first question for you. Uh, so like we'll be dealing with the set of the questions. So you can ping your answer in the chat box, and finally at the end we'll be discussing those questions. And similarly, we'll be having discussion for all the questions which will be coming further today. If you feel like you want to have a discussion about any part at any instance, so just unmute yourself, or you can also ping your query in the comment section, sorry, in the chat section, and then we will have a discussion about that part. So here is the first question for you. Which is the primary source of the parent material for alluvial soil? So you need to select one of the correct options among all these possible options. So among all these four possible options, which is wind-blown sand, volcanic activity, glacial deposits, or let's say the river deposits, which is the primary source of parent material for alluvial soil? You can ping your answer in the chat box.
Sir, it is a river deposit, sir.
Yes, Sumant. So we'll see on that. So meanwhile, you can ping your answer in the chat box. So after let's say 2-3 minutes, we'll see the answer and have a discussion on it.
Sir, can you admit Sumant Kaur?
Sumant Kaur,
He joined now.
no, he has raised his hand. Like,
Okay, okay.
yeah, I think I have admitted all the people in the here. Yeah, everyone is here. That's right. ठीक है. I guess we can check the answer. Yeah, so the answer is correct, which is a river deposit. So many of you have given, yeah, so it's a river deposit which is a primary source of the parent material for alluvial soil. So usually the composition for the geological material, which is the alluvial soil, is being led up by the various sediments which has been flown through, let's say, a particular span of time, and it is get deposited, let's say, at a certain section of your uh, river path, and that basically lead to the formation of your alluvial soil. So for this particular question, the correct answer is yes, it's a river deposit. So it's a straightforward question. If you guys have any query, please raise your concern. As we can move to the next question. Yeah. So which is the correct option from the following for the degree of saturation in soil mechanics? So how do you represent the degree of saturation? Yeah, so let's check the answer. I think some of our learners have mentioned some answer B is the answer. That is the ratio of the volume of water to the given soil mass. Yes, let's check this. Yeah, so the correct option is option B, which is the ratio of the volume both parts. So usually, if you see our soil composition, so I think it's very fundamental. Then also I want to highlight that. So your soil matrix basically composed of with some of the fluids in between, and then you also have some, let's say, air voids. So in this case, uh, how do we represent a degree of saturation? So basically it intend to highlight like how much your soil is basically having a moisture in this. So to represent that, we usually come up with a certain parameter, and that is known as the degree of saturation, which is basically given by volume of water, which is represented by VW, and then you are having the volume of solid. So this particular ratio basically give your degree of saturation, which basically shows like how moist your soil matrix is. Moist in sense like from a water part.
Sir, it is VW by VV.
Oh, sorry. Yeah, sorry, my bad. Yeah, it's a volume of voids. Sorry. Yeah.
Yes.
So your volume of voids is basically represented by VV. So H is equals to VW by VV. Yes, guys. So any doubt in this? So in this case, just to brush up again, your volume of water is represented by VW. Then you are having volume of voids by VV, and then volume of solids, which is your soil particles, is represented by VS. Similarly, your weight of water will be WW. You won't be having any weight of the air words, uh, and then you are having weight of solids. Yeah. So let's move to the third question, guys. Any discussion on this? If you want to have, okay. Then. Moving to the third question. So you need to represent how we can basically highlight the coefficient of the uniformity. So you need to show the coefficient of the uniformity. What is the particular relation which we use? So in our today's class, you guys might be thinking like we are brushing up with the, we are taking very fundamentals. So, but it's important for you to have a small revision on this so that in our further class we can have questions which are related to your foundation. So these initial fundamentals are required for you to check upon. We are having answer from some people. You can also refer the Professor Bedia's lecture notes if you have. So he might have shown some of the relations in that. I'm not sure whether he has covered fundamentals or not in his lecture slides, but in case if he has covered, you can refer them. Or yeah. So yeah, let's check the answer. The correct answer is option D. Yes, Suman. So D is the correct answer. Uh, because yeah, another one might represent, let's say, coefficient of curvature, which we will see at a later stage. But let's see about the coefficient of uniformity. So usually, let's say in a soil matrix, uh, so your soil matrix basically composed of, let's say, very large particles. I don't know what is very large, but just for the reference, let's say for having a comparison, these are very large particles. Then you are having smaller particles, or let's say large particles, and then you are having the small particles, and then you are having very small particles, large particle, very large particle, small, very large, small. So that's how your soil material is. So it's not having a, usually if you go to any site and if you take a certain amount of soil, means in at most of the sites you don't find a uniform uh, size of soil particles. So in this case, let's say, to get to account for this type of parameters, to account for this type of parameter, we usually deal it with the, let's say, the sieving. So where we basically uh, dig out the soil, like we build a plot. Sorry guys, there's issue with my, I think. Yeah, yeah. So to account for this parameter, like for our different size of soil particles, we do the grading of the soil. So where basically we do the sieve, we perform the sieve size analysis of different particles, and then we obtain the different particles which have been written on the different size of the sieve. And after that, you basically get a curve which is basically represented by gradation curve, and I'll just show you how basically it looks like. So the curve is, yeah, so that's how basically your C gradation curve basically look like. So in this axis we basically plot the uh, particle final on the y-axis, and on this axis you basically represent the size of particles, right? We usually represent that in the logarithmic scale, and somewhere that's how your curve basically looks like. And then from here you need to take the so this particle final are represented in the percentage, and on this axis basically you need to take the 10 percentage particle final, and then you need to take the corresponding size of the particle which is usually represented in the logarithmic scale, and then similarly you need to go for the 60%, and then let's say for the 10%. So this is basically, so this particular uh, size of the particle will take, which is the d60, and then this is your d10, and that's how you'll get the coefficient of the uniformity, so which is your d60 by d10. So cu basically, so if your cu value basically comes out near to 1, then we can say that your particles are usually uniform of nature, so your soil matrix are consisting of the particles which are having a uniform size. So that's how you can account for the, let's say, the different size of the particles in your soil matrix. So the one parameter which can help you in accounting of that is your coefficient of the uniformity, which is the d60 by d10, and with the help of the gradation curve you can obtain that. So any doubt in this, guys? Okay, if not so, then we can move to our next question, which is question number 4. How do you define the effective stress in the soil? Yeah. So let's check the answer. The correct answer is total stress minus pore water pressure. Uh, it's a very fundamental but very important thing in the soil mechanics. So usually your effective stress is basically represented by the sigma dash, and then it's very famous relation, which is sigma, which is your total stress minus pore water pressure. So that's how your basically soil stress are represented by. So just to have a look upon this, so let's say again come to our soil matrix, and in your soil matrix, if you want to determine how much is the stress available here at this point. So uh, just to have a I want to have a answer from you guys. Okay, whatever I am writing, it's not showing you. Wait a second. Yes, guys. So the correct answer is option A, which is your pore water pressure minus confining pressure. Sorry, pore water total stress minus pore water pressure. So usually stresses in the soils are represented by the effective stresses, and it is basically a very famous relation in geotechnical engineering, which is your total stress minus the pore water pressure. So just to, like, if let's say if I'm having a certain soil matrix available with me, and if this is the particular reference point, let's say if I want to talk about not reference point, but let's say a point of our interest. So for this point of our interest, what all stresses are acting here? So can anyone want to answer that? So usually our soil matrix is consist of both your uh, air voids as well as the water inches. So at a certain point, what all stresses are available? You can point your answer in the chat box. Okay, I'll answer this. So usually at any point of our interest, you'll be having the pressure, let's say from the soil mass, or let's say from any load which is coming from the superstructure above the soil. So that will basically impart uh, load at this particular point, which will lead to a certain stress, which is your normal stress, and which is basically represented by your total stress. And then also this particular stress will be uh, counteract by your hydrostatic stress, which will be offered by your water particles beneath your soil particles, and that will impart pore water pressure. And to have a to account for both of these stresses, we usually represented this parameter with the help of the effective stress, which is known as the sigma dash, and thus its sigma dash minus sigma u will basically give your total stress minus pore water pressure, and it will give you effective. So the correct answer is option. Any doubt in this? So moving to our next question, question number 5. In the Moore-Coulomb failure line, what is the intercept on the shear stress axis represents? So we are having a Moore-Coulomb failure available with you, and what is the intercept on the shear stress axis represents? So if you guys can recall, we usually perform a certain type of test to account for the C and the phi parameter of our soil, which is a very famous test known as the Dirac shear test. And to obtain the parameter, let's say for the C and the phi, we plot a certain result, and then with the help that plot we obtain those parameters. So concerning, coming back to our question, what does the intercept on the shear stress axis represents? Hello, you guys can hear to me, right? Yeah, okay, okay. So let's look to this. So yeah, we are having answer from our people. So those who are new to this concept, let me tell you in a very simpler terms. So let's say if you are having a certain soil matrix available with you, and let's say if it's subjected to certain amount of normal load, and there will be some, and let's say if I take out a particle, two particles, so in this case your particles will be having a certain amount of normal load which will be acting on that, and also within your particles you will be having a shear force which will be acting along the surface of your particle, soil particle. So this is represented by tau, and your normal is basically represented by sigma n. So to account for the failure of this soil mass, so usually we take a certain, if I'll go with a different color, yeah. So let's say if I take a certain element out of this soil matrix, and this matrix basically will be having a this small matrix which I have taken from the big matrix. So how big this particle size, the element size, it depends on our engineering judgment, like what do you want to account for. So in this soil mass, if I want to define the failure, like whether this element which are having a soil particle in this, and this matrix when it is subjected to some external load, whether it has reached to its failure point or not. So we basically perform a Dirac shear test, uh, and it basically gives us a certain type of plot, and on y-axis you basically have a shear stress, and on the x-axis you will be having the normal stress. So if you remember the uh, like this particular type of plot, this more plot we basically say, and where you basically will be having a set of the normal stress and the shear stress, and this basically will be and there will be a certain failure line which will account for your failure of the soil mass. So let's say this particular element will be having subjected to your normal load, and you will be having the shear stress as well, right? To account for the failure of the soil mass which is subjected to this type of stresses, we usually plot this combinations of the stresses on the certain plot, where you'll be having a normal stress on the x-axis, shear stress on the y-axis, and whether your this particular element has reached to failure or not, it depends on this particular plot. And if this plot basically crosses this particular failure line, this is basically known as the Mohr-Coulomb failure line. And this is your C, and the slope of this line basically is the phi. So the very famous relation which is known as your tau is equals to c plus sigma and tan phi, right? Am I right? Yeah, your tan phi. Yeah. So this is your particular plot. So your shear stress will be basically represented by the cohesion with the normal stress multiplied with your tangent of your uh, inter tangent of your this particular angle, and which is known as the friction angle, and thus your y-intercept on the shear stress axis is basically your cohesion. So this C basically account for the C, and this phi is basically your the friction angle. So with the help of the direct shear test, you can obtain this plot, and this intercept on the y-axis, which is on the shear stress axis, basically represent your cohesion, and the slope of this particular Mohr Coulomb failure line basically represent your friction angle, which is a phi. So that's why the intercept on the shear stress axis represent your cohesion. So the motivation of drawing this particular part, because I think you guys might be aware of, like, let's say we used to perform the direct shear test and then we obtain the this particular C5 plot, but let's say at the physical level what is basically happening to represent that, I have plotted this, and then I wanted to highlight the how this element is subjected to the normal stress and the shear stress, and how you can identify the various parameters which are subjected to this particular relation, which is your tau equals to c plus sigma and tan. So it was again having various complexities, but to define in the simpler terms, you can understand this y-intercept basically represents the cohesion, and the slope of this line is your friction angle. Any doubt in this, guys? So the correct answer is the your cohesion. And if you are having a doubt in this, please discuss, else we can move to the next question. Okay, so let's move to our next question. So this is a question. So in a natural condition, you are having a soil sample which is having a mass of 2290 gram, and then it's having a volume of 1.15 in 10 to the power minus 3 meter cube. After being completely dried in an oven, the mass of the sample is reduced to your 2035 gram. The volume of the specific gravity we know is the 2.68. Then you need to determine what is the water content of the soil. So you need to have a little idea about the index properties of the soil and the various relations concerned with those index properties, and then you can answer this particular question. Yeah, I think Sumant has given the explanation itself in the chat box. So let's look to the answer. The correct answer is 12.5. So usually your water content is basically represented by your weight of water to your weight of the solid particle. To obtain to obtain the weight of the water, we usually perform the oven test, where we basically dry our soil sample and we take the mass of the soil sample before oven drying and the mass of the soil sample after the oven drying, right? And so we usually take the, and that basically the difference of that basically will give you the weight of the water. So in our case, to obtain this, you'll be having the 2290, which is your initial bulk mass. Then after the oven drying, then it will give you the dry mass, which is your 2035. And again, since your water has been evaporated from the soil, so the only mass in your soil bulk soil matrix is your solid mass, and this is basically your 2035, and that basically is will give you something, let's say 0.125, and in the percentage basically it will be 12.5%. So the correct answer is option B, which is your 12.5%. So yeah, it was a straightforward question. You just need to know the definition of your water content. Any doubt in this, guys? Okay, if not so, then let's move to our next question. Question number 7. So for this particular problem, please determine what is your degree of saturation.
What are the options, sir?
Okay. So these are the options. Yeah. So you can refer the data at the back. So this is your water content. GS is 2.68. And then you need to determine what is the degree of the saturation. So let's check the answer. The answer is option C, 64.5. So how did you guys solve this? So which particular relation we need to go for?
GW is equal to SE.
I see. So how you will evaluate the void ratio in this case? So you are having W.
Using a gamma dry formula.
Yeah. How do you account for that? So it's basically gamma dry. How do you represent that?
Mass of the dry soil
Hmm.
2035 grams divided by volume 1.115 into 10 power minus 3. That gives you gamma dry.
Okay.
We equate this to the G gamma W by 1 plus C.
Yeah.
G is known to you, gamma W 1 gram per cc we assume.
Hmm.
Then we can get a void ratio of 0.514.
Yeah. So first you got the gamma dry, and then with the help of the gamma dry, you got the void ratio, right?
Void ratio is.
What is the gamma W you have taken? 9.81?
It is 2035 grams divided by
Gamma W, sorry.
gamma W 1 gram per cc, no option. Because I converted everything in gram per cc,
Okay.
therefore 1 gram per cc I have taken.
Any other way, guys, you have taken? Okay. Yeah. So let's solve this. So usually with the help of, there's a very famous relation which is your ES is equals to WG, and where E is your void ratio, S your degree of saturation, W water content, G is your specific gravity. Now how you will account for the E? So there's another relation which is known as the gamma dry, which is your G gamma W upon 1 plus E, right? And now here comes how do you calculate the gamma dry. So G gamma W 1 plus E we know. So gamma dry is your none other than your weight of the dry soil to the initial volume, right? So it's your basically 2035 and your initial volume is 1.15 into 10 to the power minus 3 meter cube. So again it's a gamma, so we can calculate the in terms of not in the gamma dry, we can calculate in the rho dry. So we don't need to take the account of the weight of the soil, we can just deal with the mass. Okay, so this is how your uh, dry density will take into account. And how much is this value? 115. Is it 1769?
It is 1.76, sir.
Yeah. So again 1.15 meter cube.
Numerator is given in gram, denominator in meter cubed is there. You will need to convert centimeter cube.
No worries. So 2035 gram, if I'll take into centimeter cube, so you just need to take into 10 raised to the power 6, and how much you will get? So 2035 1.15 into 1000,
1.765, sir.
1.765, right?
Yeah.
Gram per cc. And with the help of that you can evaluate your void ratio, which is your G gamma W upon gamma dry minus 1, right? So your EE, you are getting it as 2.68, 1.765 minus 1, right?
No, sir. No, sir.
So something is wrong.
G into 1 by gamma D minus 1. Gamma D should come down.
Yeah. So G gamma W 1 plus E. This is a relation, right? Gamma dry G gamma W upon 1 plus E. Aha.
So in the formula, what you have written on the left hand side, that's correct, sir. Formula correct only.
Yeah, yeah, yeah.
Formula correct only, sir.
So gamma dry is your E is equals to G gamma W upon gamma dry minus 1. Okay, it will come into denominator.
Denominator it will comes.
Oh, sorry. 1.765. So your void ratio is coming out as a 0.518, right?
Yes, sir.
And then you can account for the degree of the saturation, which is your none other than S is equals to Wg by E. W you have evaluated already, which is your 0.125, and G is your
2.68.
2.68, and your void ratio is 0.518. So your answer is none other than 64.64, which is your 64.5%. Yeah. So the correct answer is option C, which is. So for getting this, sorry, I made it mistake here, like in the calculation part. But yeah, the relation the two major relations which you have to use is the ES equals to WG and gamma dry equals to G gamma W upon 1 plus E. And with the help of that, you can calculate this. Moving to the next question. Yeah. So your sand is having a maximum dry unit weight of 20.5 kN per meter cube, minimum dry unit weight of 16.2 kN per meter cube. The sand in the field has a moisture of 9% and the relative density of the 60%. The moist unit weight of the sand in the field is. So please calculate this. So let's check the answer. The correct answer is option A, which is 20.2. So usually your relative density your RD is basically represented by uh, E max minus E, which is your E maximum is your maximum density at a site, then you are having E max minus E minimum, right? And then your relative density is also represented by 1 upon gamma minimum minus 1 upon gamma 1 upon gamma minimum minus 1 upon gamma maximum. Is it right? Okay. Gamma maximum, gamma minimum, gamma maximum by gamma, gamma minus gamma minimum, gamma maximum by gamma
It's correct, sir.
correct, right?
Yeah.
Yeah. So with the help of this particular relation, we can find it out. Suppose your related density has been given in this particular terms, which is in the terms of the unit weight. So your relative density is none other than 1 upon rho minimum minus 1 by rho, 1 upon rho minimum and minus 1 by rho max. So your relative density is given in terms of 0.6 and 1 upon rho minimum is your 16.2 minus 1 upon rho, you need to find it out, and 1 upon rho minimum is your 1 upon 16.2 minus 1 upon rho maximum, which is your 1 upon 20.2. So yeah, this rho will basically give you uh, so with the help of this particular relation, just circulating the terms here and there, and then you can get the value of the rho. And the correct answer is it A? So you guys are also getting the same.
No, sir. One more step is there. We get rho dry now. All these are dry unit weights.
Okay,
In the
okay.
formula, what we are writing is all of them are dry.
Dry unit weight. So this will
Yeah,
be your
that we need to multiply with the water content to get the bulk unit weight.
got it, got it. So with the help of this, you will get the rho dry, and once you get the rho dry, you need to get the moist unit weight, and with the for that we need to multiply it with the moisture content, right?
1 plus water content.
Yeah, 1 plus which is the 9%, right?
Yes, sir.
Yeah. So for your rho moist will be your rho dry 1 plus water content. And you can also look, like, I don't remember these relations directly, so I go with the initial relations. So and then you can derive to this, but yeah, since our learners already know this, so we can go with this rho moist to rho dry into 1 by water content. As you can just go with the particular relation as well, where your very famous relation 1 plus E, and then your G 1 plus ES. With the help of this also you can derive the thing. Yeah, gamma W is also there. So with the help of this you can also apply that. move to our next question then. Question number 9. The void ratio of the samples basically decreased from 0.92 to 0.81 in a laboratory consolidation test when the pressure was raised from 2 to 3.5 kilogram per centimeter square. The coefficient of the volume change is, so you need to find out the MV value. Hello. Hello. Hi Pratik. Pratik. हाँ. हाँ. ठीक है मैं इन्फॉर्म कर दूंगा. हाँ. अच्छा. वो समाध्या सर के जो स्टूडेंट है आशीष. ओके. ठीक है. श्योर. तो क्या वो पोर्टल के थ्रू होगा कि कैसे? अच्छा. डन. हम्म. अच्छा ठीक है. तुम लोग हमको बता देना जैसा भी रहता है. चले जाएगी. मैं इन्फॉर्म करना. हाँ. ओके प्रतीक. ओके. Yeah, so let's check the answer. What do we have from our learners? We have option D. So yeah, 0.038. Sumant has given the answer D. Yeah, answer is correct. So which is option D. So Sumant, how did you solve that?
Sir, initial variation minus final variation divided by initial pressure minus final pressure, sir.
Mm-hmm.
That is that comes to AV, sir, volume of that is. Then you are calculating volume of mass, sir. AV by 1 plus T0.
Mm-hmm.
Then
So
automatically come T0 as given 0.92.
mm-hmm.
Then the answer come divided by 1.92. Then it comes to 0.02 centimeter square per kg, sir. That's all.
Okay, so yeah, we'll take the similar approach. So your MV is none other than delta E, changing the void ratio to a delta sigma, and then we'll be having 1 plus initial void ratio. So that will be your 0.92 to 0.81, and then your delta sigma is none other than 3.5 minus 2 into 1 plus the initial void ratio, which is your 0.92, and how much it is coming out as 0.038.
Yes, sir. Yes, sir.
Okay. So usually, like whenever our soil is subjected to some external load, and let's say if you want to account for how much volume change has been taken place, so we can basically use this particular parameter, which is your MV, into account to calculate your volume change, and it is basically none other than is the coefficient of the volume change, which can take account of your volume change, which is delta E by delta sigma into 1 plus E naught. Moving to question number 10. So it basically concerns with the calculation of the effective stress. So your groundwater table lies 4 meter below the surface with a granular soil deposit 6.5 meter deep sitting above an impermeable layer. Then at 3.5 meters, the effective stress is, so you need to calculate what is the effective stress at the depth of the 3.5 meters. So let's check the answer. The correct answer is 59.1. Yeah, it's option B. So as mentioned, the groundwater table lies 4 meters below the surface. So let's say this is your initial reference line, this is your 4 meter with a granule, and this is sitting above an impermeable layer. So overall your granular soil depth is your 6.5 meter. So let's say at 3.5 meter, your effective stress measured you need to calculate. So here is your water table. So okay, it's straightforward. So you know sigma dash is none other than your sigma minus u, right? So at 3.5, okay, you need to calculate the unit weight. So for bulk unit weight,
The dry unit weight of soil into depth of Z is 3.5.
yeah, but you need to find the dry unit weight
Dry
as
unit of weight, sir.
yeah,
Specific gravity into dry unit weight of water
hmm,
divided by 1 plus into Z. That will come, sir.
so 1 plus c, right?
Yes, sir. Yes, sir.
So how much it is coming out as?
16.9, sir. Approximate.
16.9. Okay, so
Then
16.9,
multiplies by the 3.5, sir. Effective stress.
right, 3.5, and then your pore water pressure is
Yes, sir.
9.81 minus 3 into 3.5.
Yes, sir.
It is pore water is zero, sir.
No, no, 4 water
But
zero, sir. Your pore water is not zero.
Okay, you have already taken the dry unit weight, so that is taking
um,
into account.
Yes, sir.
Okay, the pore water pressure is 0. Yeah, the water table is at the 4 meter. Yeah, so your u minus 0 into 3.5, and then how much it is coming out as it? 59.1.
15.143. Right, sir.
Okay, okay, kilonewton per meter square. Yeah, so you just need to know this relation in this particular question, nothing else. So sigma dash is equal to sigma minus c. Even I am able to, even I am recalling so many relations now, though we are involved in so many advanced research in our lab, but yeah, we are not in that touch with our fundamentals. So though we have learned it, like this is very core of our geotechnical engineering research, but yeah, it becomes very necessary to recall with time. So moving to question number 11. Okay, it's again straightforward. You can do this. ES equals to WG. Yeah, you can do, yeah, answer this question number 12.
sir, a small query in this question.
Yeah, sure.
Recently, I attempted this question in one of the mock tests.
Okay.
What happens is if the sand is in its dense state is mentioned, but they have not mentioned very dense state.
Very.
Very dense. Very dense state means then only the answer will come as 100%. For dense state, we cannot define what is the value of this.
No, but they are asking the relative density of sand is close to, like, you can never
Yes.
achieve the 100% density.
But very close means see actually it should be very dense state. Question normally we have a five states.
They are asking the
Loose,
densest state. So will that take account of very dense? again it's a different nomenclature, but
Mhm.
can it be related to your part which you are saying?
Normally in correlations table,
Yeah, yeah,
they give a five correlations.
yeah.
Starting from very loose only RD is equal to 0.
Okay.
Then after that loose state,
Mm-hmm.
it is ranging from 0 to 15,
Mm-hmm.
something like that. After that it goes to medium, then it goes
Mm-hmm.
to dense. Finally it goes to very dense state, then only RD is 100%.
Okay.
This
Yeah,
that's
but
what it is.
it's saying the densest. So I think it's accounting for very dense stage only, which you are mentioning.
Okay, sir. Then
Yeah. So in this case, as ARV mentioned, so very dense or densest, both can be uh, taken into account here. So this will be your 100% B. Moving to question number 13. Yeah, you can answer this. Yeah, in this question, if we see, they are asking like they have mentioned the effective stress at a point 10 meter below the ground, which is the 80 kPa. So when water table was at the ground surface, the effective stress was 80 kPa, and now it has been lowered by 3 meter. So you need to mention what will be the effective stress at the same point. So first of all, if I lower the water table from its initial stage, so whether the effective stress will increase or decrease. So let's say in our case, this is your water table, and let's say if I'm talking about this point of our interest, and this is your initial reference line, which is your ground level. So now if I lower this, sorry, Mhm. So let's say if this is your soil element, so it's having this sigma dash as some effective stress. So if I lower this water table, let's say by a certain level, so what happened to your this sigma dash, whether it will increase or decrease? It will increase, right? Because since this water table is lowered, so whatever pore water pressure which was acting on this is also getting lower, and due to that, since we know the effective stress is sigma minus u, since this pore water pressure is lowered, so your sigma dash will get increased. Now how much it will get increased? So uh, the decrement in your pore water pressure will basically represent your increment in the sigma dash, right? So your del delta sigma dash will be your delta u in this case, and your delta u is 3 taking into 10, so delta sigma dash, so which is your 30 kPa. Your initial, so your sigma final will be sigma naught plus delta sigma dash. So sigma naught is how much? Your 80 kPa plus delta sigma is 30. So this is none other than 110 kPa, right? So correct answer is option B. So it will be increased to 110 kPa. Any doubt in this? Okay, so I think our with this question will reach to the conclusion of our today's session. So if you guys have any query, please feel free to ask. And if you don't have anything to discuss, then we can call our day today and we'll meet next Tuesday. So just a little information. So I'll be uploading these videos to a YouTube channel, and I'll also be uploading the PDF format of this presentation to a Google Drive. The link of both YouTube channel and the Google Drive will be shared to you by the NPTEL team. So in case if your friends are also enrolled into this particular course, you can ask them or you can share, you can basically inform them to go through this content if they are interested. Also it will be helpful for you, let's say at a later stage, if you want to come back to a certain discussion which we have today, you can refer these things. So in our today's class we just touch upon very fundamentals. Further we'll look into more into the foundations engineering part and how which is highly relatable because it basic directly deals with your field application. Yeah, yes, ARV, please.
Sir, in next class, can you spare some 5 minutes about BRMF scholarships regarding that
Sure, sure,
procedure?
sure, ARV, sure, no worries.
Right, sir. Thank you.
I'll let you know. Just remind me.
Yeah, okay, sir.
Okay. Yeah, yeah. Oh, sure. Okay, guys. Then if there's nothing to discuss, we can end our session today. Thank you so much for joining. We'll meet on next
Sir,
Tuesday.
one
Yeah, yes, yes,
sir, one
please.
request. Sir, one request. Sir, one request. Kindly, this class will start 7 p.m. or actually, then it is helpful to us.
Okay. Uh, Tapan, actually, the timings are already decided and it has been circulated throughout the learners of the course. So it's a standard timing. So I don't have any say in this. It has been decided by the NPTEL team only. But don't worry, like anyway, I'll be uploading the recording of the sessions on YouTube channel. So let's say for the next 1 hour, which you are mentioning, from 7 to 8, you can attend on live, and for initial 6 to 7, you can watch refer the YouTube recording. And if you have anything to discuss about that, if you have any doubt in that particular section, you can post your query in the comment section of the YouTube video. I'll definitely address that, or let's say we can also discuss in the further class. So is it all
Okay,
right?
sir. Okay, okay. Thank you, sir.
Okay, Tapan. Okay, no worries. Anything else, guys? Okay, then let's end our session today. We'll meet on next Tuesday at 6 p.m. Thank you so much for joining.